Thank you very much. Today I'll be talking about VirtualGhost, which is a system built using LLVM to protect applications from a compromised operating system kernel. This is joint work with Nathan Dontenhan and Vikram Adve, who are at the University of Illinois at Urbana-Champaign. And speaking of the University of Illinois, as most of you probably know, for a long time I've been with the LLVM research group at the University of Illinois. But recently I graduated, and now I am an assistant professor at the University of Rochester. Thank you. All right, so talking about VirtualGhost, we start by asking the question, do you trust your operating system kernel? And some of you may say, John, don't be ridiculous. Of course I do not trust my operating system kernel. It's written in C and it's bad. Well, we may think that we do not trust our operating system kernels, but in fact, in practice, we do. We use them to buy things online using our credit cards, or if you're like me, your debit card. Filing our taxes, which contain our social security numbers. Our medical information is stored on commodity operating systems, so all the notes that our doctors are taking about us are stored on these systems. Voting machines. Some voting machines use Windows CE, or at least they did a few years ago. And even national security, the three-letter agencies that we all know and maybe love, have been increasingly wanting to move to commodity operating system kernels because these kernels provide better return on investment. They're the operating system kernels that everyone else is paying money into to use, and therefore they can take advantage of those benefits. But commodity operating system kernels, as I hinted at before, are vulnerable. They're vulnerable just the same way that regular C and C++ applications are to attack. They can have buffer overflows, which can overwrite control data or non-control data. They can have integer overflows, which can be used to either corrupt memory or to cause other sorts of undefined behavior to occur. They can have information leaks. So an application-sensitive information may be stored within the operating system kernel, and through a bug, the operating system kernel may allow other applications to get access to that information, to get a copy of that information. And then finally, there's kernel-level malware. So if an attacker is able to get into the administrator account or the root account on a system, that attacker can actually extend the operating system's functionality to do malicious things, such as hiding processes or, worse, stealing information or modifying application information through the operating system kernel. And here's the real kicker. The real kicker is that if an operating system kernel is exploited, then all of the security guarantees on your system are null and void. You have no security if you do not have a secure operating system kernel. This is because your security guarantees are either being enforced by the operating system kernel itself, or they're being enforced by an application running on top of that operating system kernel. But with the control that the operating system kernel has, it can modify the application's control flow and data flow in a way to shut down that security guarantee. So in our research back when I was at Illinois, we built VirtualGhost. And VirtualGhost is a system that protects application data and application confidentiality and integrity from a compromised operating system kernel. It is, I believe, the first system to do this using compiler techniques thanks to LLVM. Because of this, it can run at the same privilege level as the operating system kernel. We do not need VMM hardware extensions that other previous systems require. And it's faster than hypervisor-based approaches such as Overshadow and InkTag. If you're familiar with those, VirtualGhost is faster. So that's the motivation of VirtualGhost. I will now talk a little bit about its design, show some experimental results, and then wrap up with some ideas for future work. So the goal of VirtualGhost is different from other systems. It does not try to protect an application automatically. What it tries to do instead is it tries to provide facilities which an application can use to protect itself from the operating system kernel. So we want applications to distrust the operating system kernel and to protect themselves from the operating system kernel. Now there's a number of features that an application will need. There are three that I'll be talking about today. The first is that the application needs private data and private code. It needs code that the operating system kernel cannot modify and data that the operating system kernel cannot read or modify. Secondly, the application needs to have incorruptible control flow. The operating system should not be able to stop your application, muddle around with its state, and then relaunch your application with invalid control flow. Third of all, the application needs some way of having a private encryption key, an encryption key that can use for digital signatures and for encryption so that when it sends data through the operating system kernel, it can treat it like an untrusted channel, like a network. So it can encrypt that data, it can digitally verify the integrity of data. But to do that, it needs a key, and we need to get that key from the executable image on disk into the actual process without the operating system being involved in that process, without the operating system being able to change that key. So that doesn't sound too hard. What could possibly go wrong? Well, there's two primary challenges in doing this. The first is that most modern processor designs allow privileged software to access all of memory. The operating system gets to configure the MMU, it gets to access all of the physical memory within the system. Operating system is basically assumed to be this all-powerful, supposedly benevolent dictator of our software system. Secondly, in order to provide the services that an operating system is supposed to provide, it must be able to manipulate application state. It does not suffice to take an application, put it in a box over here, and then take your operating system, put it in a box over here, and never the two shall meet. It doesn't work that way. If you did that, your operating system kernel would not be able to create new processes or threads. It would not be able to execute new programs. You would not have an exec system call. You wouldn't have signal handler dispatch. And these are all features that we want out of our operating system kernels. So we need some way of being able to control how the operating system kernel manipulates application state instead of keeping the application completely isolated from the operating system kernel. So what do? We have virtual ghost. Instead of compiling the operating system kernel code to native code, what we do is we compile it to an intermediate instruction set, the SVA instruction set, which is based off of our beloved LLVM intermediate representation. This virtual instruction set that we're going to compile the operating system to is going to be designed to be easy to analyze and instrument, so we're going to be able to use compiler techniques to control operating system behavior. Now, the LVM-IR, pure LVM-IR without the inline assembly code support is not going to be able to run an operating system kernel. So we need a new set of instructions to add to LVM called SVOS. This is going to replace the inline assembly code in the operating system kernel and give the operating system kernel the ability to manipulate application state and to configure the hardware, doing things like MMU configuration, setting up interrupt handlers, that sort of thing. Now, the astute observer will note that you can't run virtual instruction set code on native instruction set processors. You need to translate the code from the virtual instruction set to the native instruction set. And some of you are probably thinking, that must be just-in-time compilation. Not so. The translation can, in theory, be done anytime you want. It can be done ahead of time. It can be done at boot time, system load time, application and operating system runtime. In our implementation, in our prototype, we do ahead of time translation because A, it's more efficient, and B, it's a lot easier to implement. Now looking in a little more detail, this virtual instruction set, again, it has two components. The first one is the SVA core set of instructions, and this is what allows us to use compiler instrumentation to control operating system behavior. It's based on the LVM-IR, so we've got source level types, we have the explicit SSA form, and this allows us to do sophisticated analysis and transformation of operating system kernel code. Now that second component that I talked about, those new set of instructions called the SVOS instructions that allow an operating system kernel to be represented completely in LVM-IR. These instructions are operating system neutral, so in previous work we ported Linux to the virtual instruction set, now we've ported FreeBSD. It allows us to encapsulate and control how the operating system kernel interacts with the hardware and interacts with applications. So we implement it as a runtime library, what we call the virtual ghost runtime library. And we can add runtime checks into the implementation of these instructions to enforce security policies. Okay, now let's look at those three properties that I was talking about and how we're going to use LVM to solve them. The first one is private data and private code. How are we going to give an application private data and private code? Well, in a typical operating system kernel, it lays out the virtual address space into two components. The first component is user space memory, which lives in the lower portion of the virtual address space. This is where the application gets to put all of its stuff. And then the operating system kernel lives in the higher portion of the virtual address space. This is memory that only the operating system kernel gets to read and write. Virtual Ghost adds two new partitions to the virtual address space. The first one is ghost memory. Ghost memory is per application memory that the application can read and write, but the operating system kernel is not allowed to read and write. Now secondly, that virtual ghost runtime library, those SVOS instructions, they have their own set of internal data structures that they're going to use to enforce their security policies and to provide their functionality. We don't want applications or the operating system kernel to read or write those data structures either. So we have the virtual ghost VM memory. This is memory that the virtual ghost runtime library gets to read and write, but neither applications nor the operating system kernel get to read or write. So how do we actually do this? How do we actually keep an operating system kernel from reading and writing memory when it is our benevolent dictator? What we're going to do is we're going to use a lightweight compiler instrumentation called software fault isolation. We're going to instrument every load and store to ensure that it is only accessing either kernel memory or user space memory. It's not going to be able to access ghost memory. Now, the advantage of using compiler instrumentation over, say, like VMM extensions or, say, playing games with your page tables is the fact that we can avoid TLB flushes. So we can leave entries in the translation look-aside buffers and gain better MMU performance. Now, software fault isolation, this prevents loads and stores from accessing our ghost memory and our virtual ghost VM memory as well. But if you have a control flow integrity violation, so you have a buffer overflow that overwrites a return address, you could potentially use that to jump around our software fault isolation instrumentation. That would be bad. So what we're going to do is we are going to use an additional set of instrumentation called control flow integrity instrumentation. This is going to be a set of checks on every indirect control flow transfer, so every indirect function call, every return from a function. And it's going to ensure that we jump to valid targets within the kernel's code segment. In this way, even if there's a buffer overflow in the operating system kernel, it cannot be used to jump over the software fault isolation instrumentation or the control flow integrity instrumentation. And therefore, we know that all of our instrumentation is going to be executed and therefore is going to protect our ghost memory and our virtual ghost VM memory. Now, a side effect of control flow integrity is that not only does it protect the software fault isolation instrumentation, but it also protects the operating system kernel from attack itself. We have a whole separate paper on Coffee, which is basically virtual ghost without the virtual ghost features, on how we enforce control flow integrity on the FreeBSD kernel. So in sort of a strange case, we actually get a 2-for-1 deal. We get to protect applications and the operating system kernel with just one set of instrumentation. Going into a little bit more detail, how does the software fault isolation instrumentation work? What we do is before every load or store, in this particular example, we have a store, we are first going to compute a bit mask. So if you will, if our ghost memory is at the virtual addresses in the slide, we can test the upper bits to see if a pointer is pointing into ghost memory. If it's pointing into ghost memory, we are going to mask some higher order bits to move the pointer from ghost memory into kernel memory. If the pointer is not pointing to ghost memory, then the mask is set to 0. We OR with 0, which doesn't change the pointer at all, and the pointer stores to where it was pointing to before. So in essence, what these 3 instructions are showing is the pseudocode that checks to see if a pointer is pointing into ghost memory. If it is, it'll move it into the kernel memory. If it's not pointing into ghost memory, then it's either pointing into user space memory or kernel memory, which is fine, and the pointer is left alone. Control flow integrity, there's multiple ways of enforcing control flow integrity. We chose to take the shortest route to implementation because we're researchers and we like doing that. So we enhanced a control flow integrity instrumentation pass from Lehigh University, updated it from 32-bit x86 to 64-bit x86. What it does is it inserts special no-op instructions into the kernel's code at every location where control flow is allowed to transfer to. So we insert these no-op labels at the beginning of every function and after every call site. And every indirect branch, such as an indirect function call or a return from a function, is going to load the address that it wants to jump to in a register, use some bit masking to make sure that it points into the kernel's code segment so that applications can't pretend that they're part of our operating system kernel. And then they're going to check and see, OK, this place that I want to jump to, does it contain one of my no-op labels? If it does, then I can go ahead and jump there. If not, we're going to take some other action. In our implementation, we panic the kernel because we have a control flow integrity violation, so we know that an attacker is trying to jump over our instrumentation. All right, so that gives us private code and private data. What about secure application control flow? How do we keep the operating system kernel from manipulating application state in a bad way? Remember, we still have to allow manipulation, but not bad manipulation. What we are going to do is when there's an interrupt trap or system call, control flow is going to be transferred, the hardware will transfer control flow from the application or the operating system kernel to the Virtual Ghost Runtime Library. And the Virtual Ghost Runtime Library will save the interrupted program state, whether that's kernel state or application state. It will save that state into the Virtual Ghost VM memory. Now, as you will recall, the operating system kernel is not allowed to write into that memory directly. So the operating system kernel cannot modify interrupted program state directly. However, it can use the Virtual Ghost Runtime Library and ask the Virtual Ghost Runtime Library to make changes on its behalf. So it can say, Virtual Ghost Runtime Library, please change the program counter of this saved program state so that it points to a signal handler. It can do that. And the Virtual Ghost Runtime Library will say, okay, is this program counter value that you're asking me to put in here, is this a valid signal handler? Did the application tell me that this is a valid signal handler? If yes, well, then I'll go ahead and make the change. If not, then the Virtual Ghost Runtime Library will refuse to make the change, which means that the operating system kernel, if it lets the application continue to run, will allow the application to continue to run in the same state that it was in before the interrupt trap or system call occurred. So in this way, Virtual Ghost is able to vet every change to application state that an operating system kernel wants to make, and it can ensure that such changes do not violate the control flow integrity of the application. Now, third and finally, we have our private code and private data. We have our secure application control flow. Now the encryption keys. Let's say that I am a software developer. I have some sort of software store online for with which I use to give people my applications or sell people my applications. If I am going to create an application that doesn't trust an operating system kernel, I'm going to develop my application code. I'm going to generate some random application public-private key pair. So the application is going to have a public key and a private key to use for encryption and authentication. And I'm going to ship that whole thing to the end user system, and that end user is going to run it on Virtual Ghost. Now there's a problem here. The operating system kernel, if it is responsible for doing the operations for the exec system call, if it can do all of those operations, we have a couple of problems. First of all, the operating system kernel could say, well, I'm just going to replace the application keys with my own keys. So if the application encrypts anything, I know what the key is and I can read it. Or it can say, well, the application comes with files that are encrypted with the application key. I can't read those, but I'll just change the code that belongs to the application, so I'm running the wrong code with the right key, and the operating system can essentially get access to the information that way. So what Virtual Ghost is going to do is every installation of Virtual Ghost has its own public-private key pair. So there's the Virtual Ghost public-private key. That public key is going to be sent to the online store, and the application developer can encrypt the application code, the application's public and private keys, and then a hash of the whole thing with the Virtual Ghost public key. And then this whole blob gets sent to the end user system. Then when the operating system kernel asks Virtual Ghost to set up the application for execution, which the operating system must use Virtual Ghost to do that because Virtual Ghost is the only thing that can change an application state to start execution, because that requires changing the program counter. The Virtual Ghost Runtime Library can verify that, in fact, the application key associated with this executable has not been modified. It can verify that because it is the only entity with the Virtual Ghost private key. So it can verify that that key has not been modified. It can verify that the application's code has not been modified. And so when it sets things up for the exec system call, it can decrypt that application's public-private key pair and put it into the application's ghost memory for the application to use. All right, so that's the basic design of Virtual Ghost. Let's look at some results. Implementation, we built a 64-bit implementation of Virtual Ghost. We used FreeBSD 9, and we used FreeBSD 9 because FreeBSD at the time, and still today, compiles with LLVM right out of the box, whereas there was some concern about whether Linux would work quite as well. And then we modified 3 applications to use ghost memory, an SSH client, the SSH agent keychain server, and the SSH add utility. Now, to test the security of Virtual Ghost, we decided to build a kernel-level piece of malware that would try a rather sophisticated attack, an attack sufficiently sophisticated that it's not really needed on today's systems, but it might be something that an attacker would try on Virtual Ghost. What this attack tries to do is it takes an application and it tries to install a signal handler that will copy data from ghost memory into the application's public memory, because the public memory is memory that belongs to the application that the operating system kernel is still allowed to access. So if a piece of malware could manage to do this, then it would defeat the purpose of having ghost memory, because it could trick an application into copying private data from ghost memory into application memory. This attack works on a regular FreeBSD system. So on a standard out-of-the-box FreeBSD system, this attack works because you don't have any of the virtual ghost protections in place. Now, on a virtual ghost system, in our experiments, this sort of attack, as sophisticated as it is, does not work. And the primary reason why is because the operating system kernel cannot change the program counter in the saved application state. The software fault isolation instrumentation that LLVM provides to us prevents the operating system kernel from being able to change application state directly. So it has to ask VirtualGhost to make the change. And VirtualGhost says, no, this change is not executing a valid signal handler. What it is doing is it's changing the program counter to some arbitrary value. And so this sophisticated attack does not work on VirtualGhost. Now, how does compiler technique compare to previous techniques? There have been previous systems such as InkTag and Overshadow, which attempt to basically magically encrypt application data by playing games with the EMMU and detecting when the operating system kernel accesses application data and magically encrypting it underneath the operating system's nose. We compared VirtualGhost's performance to InkTag's performance. We looked at the latency of system calls via the LLVM benchmark suite. Now, full disclosure, this is not an apples-to-apples comparison. InkTag did experiments on Linux. We used FreeBSD. The version of the LLVM benchmark suites that each of us used are different, so this is more of an apples-to-oranges comparison. Still, it gives us a rough ballpark, and what we see is that VirtualGhost is a lot faster than InkTag. It's a lot faster. So InkTag, the overheads are oftentimes about 7x to 9x. VirtualGhost typically tends to have more like 4x overhead, and for some critical benchmarks, such as page faults, it only has 15% overhead. So in terms of performance, compiler instrumentation seems to be doing pretty well. Well, all right, that's just micro benchmarks. That's latency of system calls. What about real applications? Well, we took a couple of network programs and decided to do experiments on those. We took the HTTPD web server, and we measured the bandwidth that we could get using Apache Bench, transferring files between 1 kilobyte and 1 megabyte in size. We configured Apache Bench to simulate 100 clients, making 100,000 requests. And what we found is that, oh, and by the way, this performance is done over a 1 gigabit per second network, isolated network. And what we found is that the performance overhead of VirtualGhost is negligible. All right, well, that's if you have a whole bunch of clients. What if you just have one client? One client that is logging into a system and trying to transfer data as quickly as possible, just one file, fast as possible. What happens? Well, what we did is we took an unmodified OpenSSH server. We ran it on the original FreeBSD system, and then we ran it on VirtualGhost. So this is a SSH server that is not using ghost memory. It's not using any of the special features of VirtualGhost. And we transferred a file between 1 kilobyte and 1 gigabyte in size. And what we found is that there's a 23% reduction of bandwidth on average, and 45% reduction in the worst case. You see that 45% reduction is basically for medium-sized files. Once your file gets large enough, your network actually becomes your bottleneck as opposed to the operating system kernel. So for average-sized files, you're probably going to see some overhead. For large-sized files, your network's the problem. All right, now what about using the VirtualGhost features? What happens if you start using ghost memory? Well, what we did is we took our ghosting SSH client. So we took the original SSH client and ran that on VirtualGhost, and then we took an SSH client that uses ghost memory and ran that on VirtualGhost. And again, we repeated the experiment where we're trying to transfer data between 1 kilobyte and 1 gigabyte in size over a 1 gigabit per second network connection. And what we found is that there's a 5% reduction in bandwidth in the worst case. Now, I'd like to add that we think that we can improve that number. What we did in order to make the ghosting SSH application work is we wrote wrapper libraries for the system calls and C library functions so that they copy data between ghost memory and traditional application memory on read and write system calls and other such system calls. If we wrote our application more intelligently to avoid this copying, because oftentimes when you're doing decryption, decrypting and encrypting has an implicit copy operation in it. So you can just do one copy instead of copying data in and then doing another copy when you encrypt or decrypt. If we optimize it, we think that we can actually reduce this overhead by eliminating these essentially redundant copies. All right, future work. One of the things that we'd like to do is we'd like to improve the performance of VirtualGhost. VirtualGhost is already doing pretty well, but we can always do better. In particular, one optimization we'd like to try to take advantage of is type safety. So in previous work on secure virtual architecture and on the Safecode compiler, utilizing type safety through type safety inference analysis sped up memory safety quite well. So we'd like to apply the same types of optimizations for VirtualGhost. The tricky thing is that since we are allowing some types of corruption, because we're only using software fault isolation, there are probably going to need to be some adjustments done to the type safety analysis. Secondly, we'd like to develop cryptographic protocols that applications can use to prevent certain types of operating system attacks. So there's already many attacks that VirtualGhost stops, but there's some very interesting and sophisticated replay attacks that may still be possible by a corrupted operating system kernel. So we want to look at methods that applications can use to protect themselves. Then finally, getting back to compilers, we'd like to see if there are ways to automatically transform applications to use the VirtualGhost features. And we think that the mobile systems environment may actually be a very amenable environment to this, because the APIs there actually communicate information, such as whether data in a file is to be shared, if it's public, or if it's private to the actual application. So exploring compiler transformations is something we'd like to do. A note about open sourcing the code. The LLVM compiler extensions and the VirtualGhost runtime library have been open sourced as of this weekend. I'm still looking into open sourcing our changes to the FreeBSD operating system kernel. The FreeBSD source code contains encryption, which kind of throws in a little monkey wrench to our ability to release it. So that's a little issue we're going to have to look at, but hopefully we can get that resolved. So in summary, VirtualGhost allows applications to protect themselves from a compromised operating system kernel. So it doesn't matter how the operating system kernel gets compromised. VirtualGhost allows applications to protect themselves. It uses compiler instrumentation. So LLVM is what made this work possible. And it allows us to use these techniques on processors that do not have special hardware extensions, such as VMM extensions that are used by hypervisors. Not only that, not only does the compiler instrumentation allow us to remove the need for special hardware, but it's actually faster than current hypervisor-based approaches. That concludes my talk, and I'm happy to take any questions.
I have two. I'll give, first one is, why is the encryption in the FreeBSD 9 kernel having you trouble releasing it?
The reason why is because I don't know what the export rules are for the United States at present.
It's open source, just like FreeBSD includes encryption.
Yes, but so there may be, so at least from what I've read, I may technically be required to file some sort of paperwork with some sort of government agency somewhere. So again, basically what it boils down to is I don't know what the rules are. If I break them, I'm going to be in big trouble. So I don't think it'll be a problem, but I need to look into it.
The other question is, I didn't see how you spoke about how VirtualGhost gets into the computer's RAM, the protections thereof, if it's pulling it off a disk, your assumptions there, and other attacks before your steady state for your Ghost runtime.
Right, that's a good question. So the question is how do we ensure that there's not a problem with bootstrapping the system? How do we ensure that VirtualGhost is actually running and not replaced by, say, overwriting the kernel image? One thing that we assume is that there's some sort of trusted platform management in place and some sort of remote attestation system in place to ensure that our code is the first code to be loaded and booted. No, not necessarily network connection. Remote attestation is proved to other systems that VirtualGhost booted first. So the TPM, though, and trusted boot is what would allow, which is the thing that would allow us to ensure that VirtualGhost is the first thing to boot on the system.
Okay, two questions for me too. Modules, Linux kernel modules. You seem to be making the assumption that the same compiler is going to be used. What if I built something with GCC that doesn't have the instrumentation built into it?
Right.
So theoretically, I can put whatever code I want in there and essentially bypass everything you've just done.
Right. So there's two things that can be done. The first one is that in the VirtualGhost design, all of the code is translated to the LVM to the LVM intermediate representation,
Right.
to the SVA virtual instruction set. So you don't ship native code. You ship virtual instruction set code, which is then translated to native code on the system. So to support, for example, loadable kernel modules, what you would do is your kernel module would be shipped as virtual instruction set code, and then the Virtual Ghost runtime library would translate that to native code. That's one way to do it. Another possible way to do it, although this is future research work, would be to try to use some sort of typed assembly language technique to verify that some compilers added the instrumentation that Virtual Ghost expects. And then that can be verified at the end user system, and then that can be loaded without Virtual Ghost having to do the translation itself.
Okay, I think I'd like to ask you more questions about that after the talk, if I could.
Sure.
Because that's actually, I work on porting the kernel to Clang, so amongst other things, that's something I'm interested to talk about more about. The second thing is that as far as encrypting an application such that it has its own key, such that the code can make it through to Virtual Ghost and be verified, it seemed that you needed to get that originally signed by an app store. So in free software, we have no such concept. So how does that work?
Right. So
Basically, it works in proprietary case, but in anything but the proprietary case, I can't see how that would work.
right. So in the case of open source software, and I'm coming up with this answer a little bit off the cuff, so if I get a detail wrong, please feel free to correct me. But the point is that someone has to generate a public-private key pair for that application.
Gen2 and Arch, everything's built on the system. For distributions like Gen2 and Arch, everything is built on the system.
Right.
So you're using the potentially compromised system in order to build the application you're going to be installing on the machine.
Right. Right. So one thing you could do is you apply Virtual Ghost to the system that you're already using. And again, you have a bootstrap problem, but we have that with pretty much any security technology that we have right now. We don't trust the machines that are sitting right in front of us. So you could potentially do that, or you could potentially use some other small system that you feel is more secure. So if you will, to split up into two parts, can you add a public-private key pair even if you're an open source software developer? Yes, that's not a problem. The question is how do you do that if you're not running a Virtual Ghost system already? You're going to have to trust your existing systems just enough to do that.
Somebody has to be trusted. The point is that you can't get rid of trust altogether.
The point is that the public-private application, the key pair for the application has to be tied to the application by some trusted party. Whether that is yourself or whether that is your application provider is a policy question. I'm sorry, I can't hear.
Maybe there's just a Virtual Ghost API that can sign applications.
But you still need to trust that in the first place. There's always a chicken and egg problem.
Yes.
Bootstrapping. First of all, nice talk. And I got a question. So you change the pointers for all the loads and stores in the kernel, and you look at all the indirect jumps. So what's the solution if something is actually malicious? So when a kernel is malicious, then you just crash, you could just panic, and that's it? Because as far as I understood it, your indirect jumps will tell you, oh yeah, it jumps to a target which is not allowed to, and then you have to do something. And if you just change the pointer with a mask, you will just overwrite your internal kernel state at some random point, and from there on, everything is off. So what are we going to do now? So are we just crashing randomly like some time after? Or?
So let me split that into two separate questions. The first one is what can be done on the software fault isolation instrumentation. So when a load or store goes bad, what can we do? So in the kernel implementation, what we do is we move the pointer into the kernel memory, because if the kernel's doing that, then it's doing something wrong already, so who cares? What you could do instead, and what would be better, is to actually reserve a portion of the address space. So you move the pointer not into kernel memory, but into this reserved portion of the address space where a write's not going to cause any problems, and a read, well, we still can't really figure out what to deal with that. So that's the first question. The second question is, what should you do if a control flow integrity violation occurs? You could crash the kernel, but then you've destroyed availability. So what you could do instead is you could potentially jump to some sort of trusted code, for example, that is going to alert an administrator that something is going wrong. So you could trade off potential violation of security for availability. You could do something like that, but then the overheads are going to change. So.
Thanks for the talk. 2 questions. First, how do you compare your compiler instrumentation with what native client does? And second, do instrument intrinsics, inline assembly, and all such?
Okay, so the first question is, how does our instrumentation compare to native client? It's essentially the same idea as native client. It's software fault isolation and it's control flow integrity instrumentation. So those are not new technologies. We've applied them simply in a novel manner. I'm not quite sure if I understand your second question. Is it about the SVOS instructions or?
The C or C++ source may have lots of intrinsics, which map to assembly instructions, or it may have direct inline assembly code in it. Do you instrument it?
So in a pure SVA / virtual ghost implementation, there is no use of the inline assembly features of LLVM. So if you wanted to add support for those, then you'd have to try to instrument them, and that would probably never be 100% accurate, which is why in our design we don't do it. In our original Linux implementation, we did not use the LLVM inline assembly language feature because it did not exist. So we know that the virtual instruction set can in fact support a complete commodity operating system kernel. For the FreeBSD prototype, we still allow some inline assembly code because we know it works, and basically it doesn't affect performance, and it's just more implementation work. So it's not a pure prototype like the original Linux prototype was several years ago.
So ultimately, to do something interesting, this application is going to have to talk to something outside of the processor it's running on. So how do you see Virtual Ghost helping to keep the integrity of that data when it's talking to something that's on a system that's not protected with Virtual Ghost, let's say, like a network or another node or whatever, something else on a network, whether that network is local or the net?
I see. So protecting other people's systems from attack is certainly beyond the scope of Virtual Ghost. What an application could do is it could use remote attestation to verify that some other system, some other program on some other system that's talking to is running on a Virtual Ghost system. So remote attestation could provide that. And an application could say, I don't want to talk to anyone unless they are also running on a Virtual Ghost system. Ghost to ghost? Yes, ghost to ghost, essentially.
Can you be more clear about a scenario where you can trust Virtual Ghost that's running your machine and the application, but not the kernel?
So the question is how can we trust Virtual Ghost and the application, but not the kernel? Is that correct? Right. So we can trust so Virtual Ghost is more trustworthy at present simply because it is smaller. It's about, I think I have it in my notes here. I want to say about 5,300 lines of code. Yes, here it is. So 5,300 lines of code is your trusted computing base. That's the Virtual Ghost runtime library plus the instrumentation libraries that are in LLVM. In future work, what I'd actually like to look at is using formal verification techniques to actually verify the implementation of Virtual Ghost to know that the implementation is enforcing the policies correctly. Now, why do we trust the application? We trust the application because if you can attack the application directly, then it doesn't matter whether the operating system is secure or not, or taken out of the trusted computing base or not. There are techniques, address sanitizer, safecode, whatever, that can be used to automatically protect applications.
Time for one last question. You just mentioned that the application code is shipped in LLVM bitcode. So I'm wondering if it's already implemented, how do you make sure that the operating system doesn't remove those instrumentations? If it's not, how can you make sure the operating system does the correct instrumentation?
I see. So how do we ensure that the operating system kernel does not remove the instrumentation? One of the things that Virtual Ghost does is it ensures that when it does its translation to native code, it ensures that native code translations are write protected. So the operating system kernel cannot just modify its own code. The operating system kernel is also not allowed to use the MMU to reconfigure its code segment to insert new instructions that way.
Let's thank the speaker again. That concludes our morning session.